Very good. Well, thank you very much, Susan, and thank you all for joining us again today. It's really a pleasure to have you on board, and I know that we've got a number of people who are repeats, and we really appreciate that. Today's webinar is another one which people have been asking for, and one that we hope has been packed with enough useful information in the limited time allotted to make it beneficial for you. Knowing full well, that we can't cover all the various permutations involved with hydronic heating in this 40 to 45-minute time frame. So we thought we'd concentrate on the primary keys for advancing the major market drivers for delivering capital investment value and improving operating efficiency. While also we have a look at maximizing the reliability of the boiler, which is working in conjunction with its integrated hydronic piping and pumping system. It's not advancing. Not advancing, Susan.
Okay, let me get it back up here and
there we go.
There we go. All right.
Now, I mentioned just a minute ago that we've got various market drivers, and I think that they can be condensed into these three that you see on the screen now: reduced energy consumption, lower life cycle cost, and LEED certification, LEED certification. Those are the three that we can condense all of these drivers in. And if I take a look at lower life cycle cost, that's a key thing that we're going to be talking about today. And when we look at life cycle costs, it boils down to a few elements, and that would be the asset life expectancy. And because the boiler is really the most vulnerable in these systems, whether it be a steam or a hot water system, it gets the most abuse. So we have to look at that life expectancy, and normally it's around 20, 25 years, something like that. And then take a look at the initial cost of that asset, and then we have to look at the operating costs. So the fuel, is a huge spend as far as the overall operational cost, but also the electrical is key. And of course we see flat gas prices today, and we're going to be concentrating on that fuel today. Flat gas prices, but electrical costs are going up. And still, even though we've got flat gas prices, significant cost contributor. Then we also have water and chemicals that we have to concern ourselves with. Yes, hot water boilers use chemicals, so that's also a cost of operation. Then, of course, there's maintenance, and there's replacement costs at the very end. Okay, so that would be the life cycle cost. As far as LEED certification is concerned, we all know about sustainability today. We're certainly triggered to that. We know that we've got finiteness in the air that we breathe, the water that we drink, and so that's why this LEED becomes so important with our design of boiler systems today, where we want to sustain, we want to conserve our fuel, our energy, and that would be electrical as well as our gas consumption. So with those then as kind of the background, this is what we're going to be covering today. Why variable flow pumping started. And here what we're going to concentrate on is ASHRAE 90.1. That's where it all started. A number of years ago, engineers got together and said, look, we've got to do something about improving the overall efficiency of these systems. We have to do something about conserving the cost. ASHRAE 90 was the catalyst to get us started. Then we've got differences in the hydronic boiler system design. We've got primary, secondary, versus something which might be new to some of you today, variable flow primary. Then we want to talk about condensing boiler technology. I want to review that. And the thing that we'd like to have you keep in mind here is there's a number of designs, and you can break them down into two separate categories. We've got high mass and then low mass. We'll be talking about that. And then, of course, the characteristics of condensing boilers. We're going to look at system comparisons, and I think right here you're going to see some oh-ha moments, and that's what we're trying to conjure up here, where we're going to review the primary, secondary versus the variable flow primary at various load conditions. This is a very, very interesting point. Then, of course, we'll have our normal summary at the end, and then the Q&A. Now, as many of you know who have attended past webinars, normally I do all the presenting. I have all the hyperbole here, right? But today we're going to deviate from that routine, and we're going to let my associate, Greg Ochtenhagen, do the presenting. And we're doing this because of his expertise in this evolving discipline of efficient hydronic heating, and this is heating of commercial buildings now. We're not talking about residential, it's all commercial or industrial applications for heating. Now, Greg has an excellent background for this with over 30 years of experience in the HVAC design and project management areas, touching on industries such as healthcare, education, research and development, and also including high-performance building designs. And as a matter of fact, he is a registered professional engineer in 13 states, a LEED accredited professional, and a GEO exchange designer. And I might also mention that he taught undergraduate engineering and graduate engineering students at the Milwaukee School of Engineering for 15 years. So, you know, I'm very confident that I'm leaving you in very capable hands today. So, Greg, it's all yours.
Thanks, Steve. Well, to get started here, excuse me, I want to make sure we go in the right direction. I'd like to start off with just talking about a basic hydronic system so we're all on the same page when we're talking about terms and all the different components. A basic hydronic system is going to consist of your heating load. These are your terminal units out in the space. Thin pipe radiation, VAV reheat coils, or larger loads such as air handling unit heating coils. They'll typically have some type of control valve. In this case, we're showing the three-way control valves off of there, so this is a constant volume system. You then have the heat generation, or in our case, the boiler. And then you have expansion compensation. This is typically an expansion tank. It's important to remember that hydronic systems are generally closed systems, so as the water heats up, it expands. If we don't have some way of accommodating that expansion, the pressures will build to an unacceptable level and damage can occur to the system. There's an air elimination device. This is your air separator, typically. It will have an air vent. We want to remove entrained air from the system. Air that's entrained will ultimately come out of solution of the water, and this will cause corrosion, scale, which will cause your efficiency to decrease, as well as even blocking flow if it's not vented properly. So that's an important part. And then lastly, you have your pumps and pipes. Those are the devices that circulate the water that's heated by the boiler to the terminal units. Now for this presentation, we're going to focus on the pumping and the boiler and not worry about the other components. While it's important how you pick them and they will drive system efficiency, we want to limit it to just those components for this discussion. Now you're going to hear me talking about primary, secondary, and variable flow, primary variable flow pumping. So let's talk about the differences real quick in the system components. You're going to have a supply and return pipe out to the system. You're going to have your secondary or system pumps. Those are going to be your variable speed pumps. Then you will have your primary pumps, or a pump for each boiler. Now, we're not going to show them on these schematics, but each one of those pumps will have a starter, a check valve so you don't have flow back through the boilers, and typically a strainer as well. You're then going to have the decoupler pipe right over in this area. And we're going to talk about that in more detail in a minute. And then finally, you're going to have a buffer tank, and we'll talk about that near the end of the presentation and why it's so important with certain types of boilers. And then lastly, you have the boilers. Now the decoupler, and here's a picture showing what happens in a decoupler. Decoupler can be as simple as just a piece of straight pipe with multiple connections. Its purpose is to provide hydraulic separation between the primary pumps and the secondary pumps so that the pumps do not affect the other pumps' operations. If the flow is matched, as you see in the first graphic here, the water simply flows through and there's no interaction between it. If your primary flow or your boiler flow rate is higher than your secondary or system flow rate, you're actually going to bring water back around, and this will cause the temperature to the boilers to increase, and we'll give you lots of examples of that in a few minutes. If the secondary flow or the system flow is higher than the primary flow, you will get flow coming back around, or cold return water coming back around, decreasing your supply water temperature out to the system. That's generally not a good thing in most circumstances, because it's going to decrease your heat output. Now, in the last couple of years, several manufacturers have taken the idea of a straight piece of pipe and come out with dedicated decoupling devices. Sometimes they include buffer tanks or air vents, as you see here. But whether it's a straight piece of pipe or a true hydraulic decoupler, you have to understand how it works and the impact it has on the system. Now let's contrast that with a variable flow pumping arrangement, and typically this is done with high mass boilers. We're still going to have the same supply and return piping. That doesn't change, and in fact the system pumps don't change. They're the same for either option. The difference here is we don't have primary pumps. We just have the boilers and isolation valves. The isolation valves are there so that when we don't need a boiler to operate, we don't have flow through the off boiler. Obviously, if we did, we would get mixing in the primary line and the supply temperature would be less than what we're looking for. Now, a few more terms that we're going to be talking about in this presentation. High mass. These are boilers that have more than 50 gallons per million BTUs. A low mass boiler, by contrast, only has 25 gallons per million BTUs, and in fact, some of them out there have less than 10 gallons per million BTUs. Outdoor air reset. I'll talk about that in the next slide, but essentially we're adjusting the set point seasonally, the set point of the hot water temperature. Delta T, this is the temperature difference between the supply and return. Now, the important thing to remember here is the higher the delta T, the lower your energy consumption. Years ago, we typically designed delta T's using systems using a 20-degree delta T. This was mostly to protect the boiler. Nowadays, if you want to design a high-performance system, you really want to be looking at a 30 or 40-degree delta T. And it's not so much that it's the delta T that's saving you energy. It is, because if you double your delta T, your GPM goes down by half. So that's going to save you pump energy, but it's also going to give you colder water to the boiler, and as you'll see later on, that's going to improve your efficiency of the system. And then condensing mode, which is any time we have a return water temperature less than 127 degrees. That's a nominal temperature. It's going to depend on the makeup of the natural gas. Non-condensing mode is any time you have a return temperature greater than 127. The important point to remember here is that any boiler will condense if that water is cold enough. It's just that some boilers, that's an undesirable condition. Now, outdoor air temperature reset, as you can see here, is resetting the outdoor air temperature set point, or I'm sorry, resetting the hot water temperature set point based on outdoor air. In this case, this is for Eastern PA, there's a design temperature of about -5. I might have 160-degree supply water temperature. All my terminal units have been picked for that temperature. However, as you can see as the bin temperature here, we don't list all the temperatures, but the vast majority, more than 6,400 hours, are well above 29 degrees Fahrenheit. Most of the time, I don't need full output from my heating devices. So I can put in a control sequence to reduce my supply water temperature as that outdoor air temperature increases. And it'll vary from maybe a high of 160 down to a low of 130. Now, Steve mentioned 90.1. 90.1 originally came about after the first Arab oil embargo and the first energy crisis in the mid-70s. They started looking at ways to conserve energy, and then continually it's been updated, and in fact now we're in version 2013. It basically tells us that we have to have variable flow pumping if our pump horsepower exceeds a total of 10. Now, while that will save us energy, and it's a good thing to do, the problem we've had in the past is that a lot of the boilers out there have not been designed for variable flow. And that's part of the reason why people began using primary, secondary pumping. So if we look at the history of hydronic systems, remember they came from steam systems originally. And in the 60s, when people started using hydronic systems in lieu of steam systems, they had to use boilers that came from the steam industry. Most of them are either fire tubes or flexible water tubes. They're very robust when used in the steam, manufacturing of steam, but they have some idiosyncrasies that don't make them as good for hydronic systems, especially high-performance hydronic systems. Fire tube boilers especially are subject to thermal shock. They cannot take a high delta T. If the delta T is too high, the tubes will expand and contract, and that's what thermal shock is. They also cannot take water that's too cold for the same reason. Flexible water tubes can take thermal shock. As you saw in the picture, the bent tubes allow for some flexibility as that cold water comes in. But what they can't do is take a cold return temperature. Again, remember I talked about condensing mode. What happens with a conventional boiler is you're going to get condensing. Now, in a condensing boiler, as we'll talk about, they're made for that. But in a non-condensing boiler, a conventional fire tube or water tube that's made out of carbon steel, the condensation is going to cause deterioration and ultimately failure of the boilers. And we can't get the high efficiencies without using condensing boilers. So, a little bit about condensing boilers. First off, there's several different types out there. And by the way, condensing boilers have been out since the early 90s. Sometimes people confuse them with near-condensing modular boilers, and they're not the same. So, the type of boilers out there are the fire tube, the modified fire tube, the cast aluminum. There are also cast iron boilers, which are really those modular boilers, but to allow them to operate in the condensing mode, they did an add-on heat exchanger. And the same is true with the copper fin boilers, and I'm sure a lot of you have seen those in the past. Because copper will corrode, they did an add-on heat exchanger. For all these boilers where the corrosion occurs, we've gone to stainless steel so that it doesn't affect the life of the boiler. Now, some key points here to be aware of. Because of the stainless steel and because of the design, there is no minimum on return water temperature. We can take 80 degrees into these boilers if we wanted to, and they will not affect them. That wasn't the case with fire tubes or water tubes. They're inherently corrosion resistant because of the stainless steel construction, and they're not subject to thermal shock or stress. This gives us longevity and reliability, and then the other benefit is their modularity. Where I may have had a 6 million BTU fire tube boiler at one point, I may put in 3 2 million BTU condensing boilers. Now the condensing boilers will only have a 5-to-1 turn down, which isn't going to be as good as the 8-to-1 to 10-to-1 on the fire tube. However, because I can stage the boilers, I actually have a 15-to-1 turn down. And not only that, if one boiler fails, I've only lost 33% of my capacity, not 100%, which is why you see these boilers growing in market share all the time. Now, this is one of the curves I really want people to focus on, because this really explains why we use condensing boilers and why we want to look at that delta T and supply water temperature. This is an efficiency curve. And by the way, this efficiency curve doesn't apply to condensing boilers. This is any boiler. If you stay above 130, you'll notice the best you can get is about 87% efficient. And as your return water temperature increases, it actually goes down. Once we hit that 130 or 127 degrees, that's where condensing starts to occur. Now, the important thing to remember here is it starts. But to maximize efficiency, we want to maximize our condensation. So the colder the water to the boiler, the better. And you can see how that efficiency curve just climbs. And in fact, if we had 40 degrees, we'd be very close to 99% efficient. The other unique characteristic of condensing boilers is you want to run them at lower firing rates. So for the same water temperature, say you have 120, you'll notice you go from 89% to 91%, about a 2%, or not, yeah, 91%, about a 2% increase. Everywhere across the range, by going from 100% to 20% firing range, you will pick up 2 to 3%. Not a major percent, it's not a major increase, but again, if you're doing your LEED certification and doing your energy modeling, every small percentage point helps. And those of you that have done the modeling and tried to maximize your points know you're scratching, just trying to dig out anything you can to improve your alternatives to maximize those points. So let's talk about low mass boilers and their advantages and disadvantages. They do have a lower first cost because they don't contain that vessel with the mass of water. There's not as much material. Because there's not a lot of water in them, they will be very quick to respond to load variations, and they're very compact. And because they're a condensing boiler, if they're operated correctly, they will have excellent efficiencies. The disadvantages, and this is all due to their lack of mass, is they need a minimum circulation. The being able to respond to load quickly is a two-edged sword. They can respond too quickly, especially if there's no flow in there, and they will trip out on their operating limit. They will also have a higher energy efficiency. It's not uncommon to see low mass boilers have pressure drops of 10, 15, 20, or 30 feet ahead. That's pumping energy you have to spend 8,000 hours a year. They can also have erosion problems. Generally, they will have more maintenance and a lower life expectancy. And finally, they will have more cycling, and that gets into the buffer tank that we're going to talk about later. Now, comparing them to high mass boilers are typically constructed more ruggedly. Because they have that mass of water, they're not going to cycle as much. That water acts as a flywheel. That leads to lower stress on the boiler, very stable temperature control, because they're not heating up real quickly. And high mass boilers typically have less than 10 feet ahead, and more typically only about 5 feet ahead. So they have minimal effect on your pump. And one of the most important things is they're very tolerant to low flow, and in fact, most of them can live with absolutely no flow, which makes them ideal for variable flow primary pumping. And compared to conventional boilers, they're compact. The disadvantages are they do have slightly more material, so they're going to cost a little bit more. They're a little bit heavier, and they're somewhat larger than the low mass boilers. Now, how do they compare? Here's a primary-secondary system. And by the way, one of the other takeaways is I'm going to be talking about low mass boilers here in this primary-secondary loop. You could do the same analysis with high mass boilers, and you would find the results to be very similar. So this is really going to be primary-secondary versus variable flow primary with high mass. Let's look at the system here, though. We've designed it for 6,000 MBH, 160 degrees out, 120 coming back. The designer used that high delta T in there to minimize its flow. That gives us a flow rate of 300 GPM. We're going to have 3 pumps running, 3 boiler pumps running, so that's 300 GPM in the primary loop. Because of that, we're going to have absolutely no flow into the coupler. The water is going to come in, go to the boilers, and then go back out to the system without ever passing through to the coupler. That means we're going to get 120 degrees back to the boilers, and that's good. They're getting cold water. And the boilers, because they're matched to the load, are all going to be at 100% firing rate. Now, one point I'd like to make, this is an idealized system. In 35 years of designing boiler rooms and boiler systems, I've never seen the boilers perfectly match the load. The more the boilers are oversized, the worse the results are going to be. Now let's assume we have the same conditions with the variable flow primary. 160 out, 120 in. That'll give us 300 GPM just like before. 120 coming back, which means the boilers are going to see 120. All the isolation valves will be wide open. And as I said, the boilers will see 120. And the firing rate's going to be at 100%. So when you compare the two, you'll see there really isn't any difference at an idealized full load operation. Now, even here in Wisconsin, where yesterday it was 8 degrees when I got up, we don't often operate at design conditions, which is -10. Like every place else, and like I showed you on that bin chart, most of the time you're well above the minimum temperature. So even though there's no difference at full load, let's look at what happens at part load. Before I do that, one other thing I want to point out. There is one difference. You look at the pumping energy. Because you have those 3 primary pumps, it's about 4 horsepower greater using primary, secondary versus variable flow pumping. So you will be saving energy, just not boiler energy at full load. Now what happens at part load? Let's look at 70%. Again, 160 out, 120 coming back. We're going to assume no outdoor air reset at this point. That gives us a flow rate of 210 GPM. Now, because we want to have a primary rate greater than the secondary rate so we get the right kind of mixing, we're going to have all 3 boilers running at 100 GPM. That gives us 300 GPM in the primary loop. What does that do for us? Well, now we have 90 GPM coming back through that decoupler. That's going to give us 130 at the boilers, not the 120 the system is designed at. The firing rate will be 75%. Again, let's contrast that with the variable primary. System isn't going to change. That's going to be 160, 120, 210 GPM. But we're going to run all 3 boilers just like on the other system. They're going to see reduced flow, only 70 GPM. And because of that, there's no mixing in the loop. The boilers will see 120 degrees, not the 130 that you see in the primary, secondary. The firing rate will also be slightly less. Now let's compare them and see how they compare. Again, inlet temperature 130 versus 120, firing rate 75 versus 70. Now the reason the firing rate is higher is the next line. The boiler efficiencies, because of the higher entering water temperature, the low mass boilers are at 88%. The high mass boilers are at 91%. So the low mass boilers have to work a little bit harder. And then finally, because of course the secondary pumps are throttling back and your horsepower is going to vary with your cube, the pump horsepower has dropped, at least on the system pumps. But the primary pumps are still running. So there's about a 4 horsepower pumping difference. Again, this chart that I showed you before, the low mass primary, secondary boilers are operating at about 87 or 88 because the water is only 130. The high mass variable flow system is operating at 120, so it's operating at about 91% efficient. We're maximizing the efficiency of those boilers. Now, so this is just the same slide. You can just see the differences again. Now let's look at 50% load with outdoor air reset. In this case, we have 150 degrees going out with 110 coming back. We've reset that temperature down because we're not at full load. That gives us about 150 BPM on the system. In this case, we're only going to run 2 boilers, which will give us 200 GPM and 50 GPM in the decoupler coming back. So again, we're going to get mixing. The boilers aren't going to see the 110 degrees, they're going to see 120. The two boilers running will operate at a 75% firing rate to make up that load. One boiler is off. Now, comparing that again, the system doesn't change. Oops. All three boilers will operate. This is critical. Here we're operating three boilers. So what happens? The boilers are going to see 110 degrees, not 120. But because all three of them are operating, they're now operating at roughly a 50% firing rate in lieu of that 75. Remember the efficiency curve I showed earlier? The lower the firing rate, the higher the efficiency with condensing boilers. So without even taking into account that they're getting colder water, we're going from about 75 to 50, we're picking up 0.5% to 1% efficiency on the boilers alone. Again, it's not a lot, but when you're trying to design a high-performance building, every percent helps. So just looking at that again with the 110, and now the comparison. 75% firing rate with 120, 50% firing rate with 110. The efficiency, we've picked up about 3% on the boiler efficiency between the colder water and the lower firing rate. And of course, one of the biggest savings is we're picking up 3 horsepower because we're still running 2 boiler pumps at about 1.5 horses each. You don't have that penalty with the variable flow primary system. Now somebody might say, well, what if we run all 3 boilers at a lower firing rate? You might think that would help because of that firing rate curve, but in reality it works against you on 2 counts. First off, you now have 300 GPM in that primary loop, so you're going to have more mixing in the decoupler, and your inlet temperature goes up from 130 to 137. That hurts your efficiency, even though your firing rate has gone down. We're now down at 88% efficient because we're no longer in the condensing mode. Secondly, I'm now running 3 pumps that are constant speed, so I've just increased my pumping horsepower. So one of the takeaways, when you're running primary secondary, you want to run as few boilers as possible, versus variable flow primary, you want to run as many boilers as possible. Now let's take it down finally, one other scenario, down to 33% load, and with outdoor air reset. So now we're down to 140 going out and 100 coming back, 100 GPM on the system. I'm going to run 2 boilers to make sure I don't have any reverse flow in that decoupler. This is also one of the toughest things in controlling a primary-secondary loop is when you stage your boilers, because of course the system doesn't sit at 33% all the time. It's going to be moving around. It's dynamic. And you don't want to be cycling the boilers too fast. Staging of the boilers is much less critical with variable flow pumping. We're going to have 200 GPM in the primary loop with 100 GPM coming back, and that gives us 120. So we've just raised the return water temperature to the boilers by 20 degrees. And the 2 boilers will be operating at a 50% firing rate. Looking at variable flow primary, again, the system stays the same, but we run all 3 boilers, and we have the true 100-degree Fahrenheit water coming back to the boilers, and because we're running 3 of them, we're at a 33% firing rate. The comparison, 120 versus 100, which look at the boiler efficiency, 96% for the high mass boilers, 92 for the boilers in the primary-secondary arrangement. And again, look at your pumping horsepower. We're using 3 horsepower more in pumping these boilers on the primary-secondary than on the variable flow primary. Now, just to reverse, so what if we shut one boiler off and match the flow rate? You might think that would save you some energy, and it does, but look at what happens here. You're using less pump horsepower, but you're still not going to be as efficient as the primary flow systems, mainly because now your firing rate has gone up to 100%. and you've lost efficiency there. One other scenario to remember, quite often as designers we add an additional boiler for redundancy so that if one boiler fails, we don't lose any heating capacity. Now with a primary-secondary arrangement, that fourth boiler doesn't really do you any good. It just sits there until it's needed. Because as you've seen, you really want to match the flow rate as closely as possible to your system rate. So at 50% part load, you would only run 2 boilers. And you'd have 1 boiler sitting at standby as well as the standby boiler. If you have extra boilers with variable flow primary at certain conditions, so I apologize for advancing there, you can make use of that boiler because now we could run water through all 4. Again, high mass boilers have no minimum flow. So we can take that GPM down by running water through all 4 of them. Our firing rate goes from 50% to 36%, and we pick up a percentage in efficiency. So that capital cost that you have sitting there is now actually making you a little bit, or saving you a little bit of money. The next 2 slides are just a quick comparison. At full load, theoretically, there is no savings. Again, I say this is at full load because typically your system and your boilers aren't going to match, and you're always going to get some mixing, and you will get a savings. Yes, you will get pumping savings, however. At 70% load, you'll see a 3% increase in boiler efficiency, which is going to amount to a 3.6% savings in fuel and a 68% savings in pumping horsepower. At 50% load, you're still going to save roughly 3.2% in fuel, and your pumping horsepower goes up to 79%. And finally, as the lower you get, your fuel savings will go up a little bit more, in this case to 4.4, but the dramatic increase is 90% less pumping horsepower. So these savings don't include anything from reduced cycling, which you typically have more of with a primary-secondary system. Key takeaways here, any scenario, we could have looked at any percentage we wanted to, and you would have seen the variable flow primary save energy both on boiler and pumps. Now, sometimes people talk about the complexity of variable primary pumping. Well, let's look at the complexity of primary-secondary. You have your system pumps, and you have your primary pumps. And remember, your primary pumps aren't just the pump. As I mentioned before, they're going to have a check valve or triple duty valve to prevent backflow through an off boiler. Typically, people put strainers on the pumps to protect them, and you have a starter of some sort. In addition, most manufacturers will recommend you have some sort of buffer tank. And you have the decoupler, and especially if you're buying a hydraulic decoupler from a manufacturer, that's a cost there. Variable flow primary, by contrast, all you have is the boiler and the isolation valves. Simpler piping, no pump, no power. So in this example, we would have about a $7,700 installation savings. And that's just for materials alone. Generally, you can save a little bit on the installation as well. Now, one thing I sometimes see in the field is people want to try and maintain minimum flow through the boilers, and they add a modulating bypass and a flow meter. I think this came from the chiller side. You know, I first started doing variable flow primary when I was designing chiller systems. And of course, chillers are very much different than high mass boilers. They require a very high minimum flow, and we needed a modulating bypass and flow meter. Boilers, that's not needed. So while you can put it in, it's just an added cost and complexity that's not needed. Now the buffer tank is something that's needed. Here's a typical buffer tank. This is from a Wessel's catalog. You can see how it fits into the system. It just has 4 pipes. In this case, this is actually one that's used as a decoupler. And here's another example, actually out of an O&M manual for a low-mass boiler manufacturer. And you can see they're using the buffer tank as a decoupler as well. The idea for the buffer tank is to provide about 10 minutes of runtime for one boiler at low fire, because you don't want the boilers to cycle. Now, speaking from experience, I've been in boiler rooms where they didn't have buffer tanks, and you would see boilers that had 12 to 15,000 starts in the first year of operation. And we talked about reliability. That's going to shorten the reliability by airing out your burner, putting extra stress on the heat exchanger. So that's why we want that buffer tank in there, so the boilers don't cycle excessively. Now, just sort of summarizing here, what are the advantages and disadvantages? Well, primary, secondary will protect the boilers. You have that minimum flow in there, so they're not going to get hot spots. They're not going to cycle too much, ideally, if you have buffer systems. They can provide pretty good control, and it will work with any boiler design. However, you have to have more extensive piping, more equipment, and as we've shown with the examples, it's going to be a much higher operating cost. Variable flow primary systems, by contrast, are simpler, only one set of pumps, simpler piping, generally a lower installed cost, and the large mass allows no need for a buffer tank and lower firing rates, and lower fuel and electrical costs. Boiler cost may be a little bit higher, but your overall installed cost and life cycle cost will be less. The other drawback is the large mass boilers may have a slightly larger footprint. So to design a high efficient hydronic system, use as low a supply water temperature as possible. 160 is good, 140 is better. Use the highest delta T as possible. Again, ideally 40 degrees or higher. If you can't do those, use an aggressive outdoor air reset to get that cold water back to the boiler. And then finally, wherever possible, use variable flow primary pumping with high mass condensing boilers. I think we're right about on schedule for questions and answers.
You certainly are. And I just wanted to, Susan, if you just go back to slide number 14, just for just a brief second here, I just wanted to add one thing to what Greg has said. Can you do that for me? Go back to the Q&A.
I can go back to slide. Let me take back control of the
14.
All right, let me get that. And I apologize for the
If we
sound
can get rid of that aggravating noise, it would be nice.
I can't tell where it's coming from. It's not coming from a panelist, and it's not coming from an attendee. So, all right, you want to go back to 14?
Please. Okay, here, Greg has covered this very, very well. And of course, what he's talking about here are non-condensing boilers or near-condensing boilers. And I put that slide in on the left for that reason. What you see on the left is a near-condensing boiler. And we've got some corrosion, as you can see. But the main thing with this is these low-mass near-condensing boilers require a minimum temperature coming back so they don't condense, pretty high excess air level, too, so they don't condense, because the higher the excess air level, the lower the dew point, okay, of that gas. Anyway, the other thing, though, really critical with these is when they condense, those fins will plug. And when they plug, you develop back pressure in the furnace, and you go to a very, very rich mix of the gas. You start to soot up and causes all sorts of problems. So what we're talking about here is extremely important. When you've got a boiler that's non-condensing or near condensing, you've got to take a look at those temperatures. You've got to take a look at those flows, or you're really going to have problems. So now let's go to the Q&A, if you would, please.